So hi everybody. How's your GodotCon going?
Good.
Okay, cool. Yeah. So first of all, thank you to the Godot people for having us here. It's been really an amazing experience meeting so many talented people. So yeah, that's always fun nerding out with some other people that might be interested in the same things that a programmer is. So that's always fun. And so yeah, the topic for our talk here is introducing 3D tiles for Godot. This is about our integration journey of this technology called 3D tiles into the engine as a GDExtension and also as an engine submodule. We will talk a little bit about what that means and what the implications of either one is. But yeah, that's basically what we're gonna be talking about today, and also some lessons that we learned along the way of integrating this technology regarding data-intensive applications and how to make Godot play well with data-intensive applications. Because 3D tiles, they take up a lot of memory, they take up a lot of processing. So yeah, that's always fun to deal with. And lastly, my name. That's really hard to pronounce, so just call me either Nef or Leo. That's all right. So speaking of, so who's this guy, right? So my name is Leonidas Neftalí González Campos. Yes, I'm Mexican. That's a long name. That's common over there, surprisingly. And I'm a software developer based in Mexico. I am a game engine developer. I used to do backend for web stuff, but then I got tired of doing the same crud every day, as I'm sure most of you could possibly relate. And like many of the people here, I'm also an ex-Unity developer. I like to say I already hated Unity before it became cool to hate Unity. So yeah, but that's maybe just me. It just takes a lot of time to do basically anything. And I'm also a game developer in my free time, if I ever get any, right? That usually means from midnight to 3 a.m., but that's fine. And I'm clearly not good at UI or design, so I apologize if there are no really pretty transitions between one slide to the other. It's not my thing, and yeah, so hopefully that's not a deal breaker for you guys. So a little bit of my background in coding. So I started coding when I was about 12. Because a friend of mine told me that you can make your own games, and I was like, oh my god, is that even possible? Games are made. I didn't know you could do that. And so I started out with Unity back when Unity looked like that, which is quite old. I don't remember the exact version of it, but we were still using single digits, so that's kind of old. And it was still supporting JavaScript scripting, so that was bad. I never really got the hang on JavaScript. So then I transitioned to C#, and I started to look into more of not only the game development side of things, but also applications in general, like how to program other types of applications that are not precisely games, how to do software architecture, things like that. And yeah, and then eventually I kind of had an itch for more lower level stuff, and I learned C++. And that right there is just the closest I could find to a graph of my mental health going down as I learn lower level languages. So yeah, the standard library is fun, said no one.
It's supposed to go up.
Yeah, that's supposed to go up. I'm surprised it didn't. Yeah. Okay. So how come this Unity dev people, this Unity guy, is making a Godot plugin? Well, that is because of Battle Road Labs. So at Battle Road, we make a one-to-one scale simulations of the Earth with a focus on architecture planning, strategy, design, and natural disaster response. And we use Godot for that, which at first when I heard about it, it came to me as a surprise because as I'm sure many of you have heard around the internet, it's like Godot has always been played as this like, oh, it's a great engine for 2D games, but you can't really do like much 3D in it, or it's like underdeveloped for 3D. And so to me, the fact that this can even run on the Godot game engine, and it's not like just barely running, it's like running. It's just a testament to the underlying technology, the optimizations that you don't even really have to think about. And it's just like great out of the box, which is pretty cool, right? So getting into the nitty-gritty of things, what are 3D tiles, right? So 3D tiles is an open standard that aims to provide a way to store and communicate geospatial data. So this means essentially just real-world data, models, and texture data. But it's not limited to just the Earth. We do have support for other types of ellipsoids, most famously the Moon. There was this like pretty fun Moon project game that was made in Unity with 3D tiles. And so yeah, it does have support for other type of ellipsoids, but it's mostly focused on like GIS applications. So some of the features for 3D tiles are that they're a format or an extension on GLTF, the 3D model format. They are interactive, stylable, adaptable, and flexible. So essentially, a 3D tile is just a GLTF with some extra JSON sprinkled on top of it, and it tells you stuff like where it would be positioned in the world, and if it has some adjacent metadata to it. And so that's how we, over time, construct the entire rendering application. They're also designed for precision to support the most demanding analytics. So that means, again, just we have all of the positions for the 3D tiles stored in actually double precision numbers, not single precision, because when you're dealing with scales as large as the Earth, you're bound to lose some precision if you want to take into account centimeters and kilometers. So yeah, all of their position are stored in double precision floats, and also in a different coordinate system called Earth Center, Earth Fixed, but we will talk about that later. ECEF, yes, that's correct. That was a pain to deal with, but that's correct. So this plugin is not alone, so it joins a larger ecosystem of already integrated solutions on other engines. So we have most famously Cesium for Unreal, Cesium for Unity, and then their standard product, Cesium.js. So Cesium, and I was kind of getting ahead of myself with this slide here, but Cesium is essentially the underlying technology that allows you to fetch this data, right? And it handles a lot of the difficult stuff, such as knowing where the center of the globe would be, and kind of identifying where every tile should be. So Cesium does kind of all of that for you, and they have a native integration on C++, so you just compile that as a library, as a static library, and then you can just link that to whatever project you're working on, if it talks C++, which thankfully most projects do talk C++. So Godot is no exception, thankfully. So essentially we can map out the Earth and render it as a bunch of streamed 3D models. So now I bet you're wondering, oh, well, yeah, we can see the Earth, but what use do we have for that, right? So here are a couple that I just found in like a span of 15 minutes of searching applications for 3D tiles. And the reality is that there are multiple areas where this technology can be applied, and not just limited to the gaming space, but also high-fidelity, large-scale simulation applications, infrastructure planning, visualization, etc. So we got some fun visualizations on that GIF all over at the left. Then we have some flight trackers. Actually, on the way here from Mexico to Boston, the plane that I was on had a little screen that you can tap and see like where your flight is going through. And I am 100% sure that I was using 3D tiles because I could like zoom into various different places that were not necessarily my destination. And I didn't have Wi-Fi, so that was my only entertainment for 5 hours. That's great. And then we have some architectural planning over here. So this, I find this to be particularly interesting because it's not only the fact that you can see stuff that's there in the real world, but you can also like try and modify it, right? And see how things are going to be laid out and how it would look, which I don't know. I think it's pretty cool and pretty useful. Then we have some satellite visualization. That's also pretty neat. So to give you an idea of the scale at which this could be, like all of these applications except for like architectural planning have been so far of like large scale models, right? So you have like flying over terrains, or you have just like visualizing a bunch of satellites all around the Earth. But it's not just for that. It can also be worked on applications at a street level, such as this one, which is just a filter for objects that are in a city, and you can actually see like, oh, I want to know a little bit more about how the electrical system is laid out, how the buildings are laid out, and you have all of these different like filters that you can use on actual data that's actually there in the real world. And again, this is not just limited to what the plugin just provides you out of the box. You can also import your own data onto Cesium and then just, go wild with it. And last but not least, we have some like drone delivery training app. I thought that was pretty cool. And it's like very street level too. That image right there, that screenshot right there, just makes me want to make a Spider-Man clone and just like swing around the buildings. I think that someone please make that. So yeah, those are a couple of the potential applications for 3D tiles. There are many more. But yeah. So for this integration, this is how the pipeline usually looks like for a 3D tiles application. So we have the geospatial data sets, which are just the collections of the models and textures, raster data, etc., that you have over on your server, sitting on the cloud. Pretty neat, right? And then it goes through the Cesium 3D tiles model. So it parses it, it streams it, it places it in the right place, and then at the end you get it through 3D engine, which in this case is Godot, of course. But again, since it's just a GLTF representation of the data, it's not bound to any like specific renderer. So you can just you can run Cesium in headless mode, actually, so you don't have to render anything if you don't want to. But of course, we want to. So and there's a little volcano over in Japan. I just thought that looked pretty cool. So the integration pipeline of the 3D geospatial assets basically means that we need a way to fetch the tile data from either an external server, a URL, or the proprietary Cesium Ion service. So we parse the model data, which it comes in raw GLTF into a mesh instance 3D, and then we render that onto our Godot scene, right? And we would also need to, of course, generate collisions for each tile, position the model in the correct coordinates, et cetera, et cetera. And so in order to do that, we have this like kind of pipeline that every single tile has to go through. And as you might imagine, that gets very computationally expensive. So yeah, that's why this also has a focus on things that we can do to make that process work in Godot. Okay, so some considerations that we made early on in the development of the plugin for it to be successful, or as successful as we can make it, of course, and well received by the community, was that it should be easy to get into a vanilla build of the engine. So originally, when we started developing this, it was an engine submodule. So that means that you had to compile the C++ with the engine. And that's great because you get a lot of performance gains on that. And also you can enable double precision and forget that precision errors even exist. After all, computers today are fast. Computers today have a lot of memory. So you can definitely take, bless you. So you can definitely take advantage of that if you wanted to. This is still available as a sub-module if you're interested in that. But we also wanted the user experience of it to be like, you go into the asset library, you click download, you get all your assets, and that's it. You just have the Earth in like 3 clicks, which I think it's pretty cool. So that's one thing, easy to get into a vanilla build of the engine. And then it needs to be integrated into a custom build to handle double precision. We just talked about that. It needs to be performant. So there's this comment on one of the Cesium forums that I read that was like, hey, can I like render this offline? And the guy from Cesium that responded, it was like, I mean, sure, you can render like some layer of it offline, but you cannot render everything offline at once, because it's like terabytes upon terabytes of data, right? So you can imagine fetching all that in like a span of 16 milliseconds, which is usually what we would want from gaming technology. Might be a little bit complicated, so it needed to be performant. We needed to also have some sample projects with example navigation controller scripts, because even though we move in the Earth like at all times, you have no idea how complicated that math is. I had to watch like an aerospatial engineer class that I saw on YouTube with like 42 views. It was incredible. So yeah, thank God for that professor. I don't know where he is, but okay. So we figured all of that for you, so you don't have to worry about that. You can extend this like sample script with your own logic. I don't know, you can make it like a flight simulator, you can make it a driving simulator, you can make AI agents on top of the surface of the Earth or what have you, right? So that's something that I already went through the pain of to give to you guys. So thank you for that. I mean, you're welcome. And then it should be easy to navigate and understand the options available to you. So this is done through something that we call the Cesium panel, which is just basically a small menu where you have all of your options to go and upload assets, import assets, and just in general make that whole experience of getting from having an empty scene to having it render something be as smooth as possible and go there as quickly as possible. So let's take on that first point. So easy to get into a vanilla build. So having to handle the gigantic amount of data that we need in a way that doesn't want to make your computer's cooling system take off like a rocket. It happened in early development, and yet still be able to just drag and drop some files into your project folder and have everything just work out of the box, called for the solution of GDExtensions, because we needed something that's performant, so we can do all of the heavy work in C++, and then just expose some basic APIs to GDScript, so that you don't have to worry about all the black pointer magic that I'm doing in the background. Trust me, there's a lot of that. And so, yeah, that's why we chose to go with GDExtensions. We're not going to make you build the engine again and again for every release. That would be bad UX. Yeah. And so, of course, for an added performance bonus, or if you want to support double precision tile sets, you can also choose to build the plugin as an engine submodule, and it will compile as if it were a core component of Godot itself. So having the plugin be written in C++ allows us to plug right into Godot as a submodule, use bindings to generate a GDExtension, and also interface easily with Cesium's native library API. So having support for both actually means that some conditional compilation is needed, since the bindings for Godot C++ are not particularly perfect, but that's fine. We just do if-defined GDExtension, and then we don't care about the rest. So yeah, here I would like to just make a small note. If you're going to go with custom builds that will give you a little bit more performance, not a significant gain to be like, oh, this took me, I took like a 15 FPS frame drop on this one part. If I just build it as an engine submodule, that will fix it. Not necessarily, because the only thing that we're kind of dealing away with here is that we're not calling the underlying VM instance for GD script. If you're not aware, for any GD extension that you make, the function calls to the bindings will not go directly to the function pointers of Godot, so you're not directly calling Godot functions. You're actually calling the bindings for GD script. So you'll just get that word cut in half if you do custom builds. So yeah, up until now, everyone good? Everyone up to speed? Cool, awesome, perfect. So let's start to fry our brains a little bit more with the build structure. So I already kind of went over this, but basically it's a compiled library. It takes Godot 3D Tile C++, which is our end of the code. It brings that in with Cesium native, and then the bindings for Godot C++. And then we take just one little component as a vendor, which is ultralight. Why? Because Godot does not support rich text in HTML. It does so in the ever so great arcane format of BB code, which was great for forums back in 2010. It's not so great now. So yeah, we do that for some HTML rendering that we need. Then, of course, we plug all that into Godot with our own custom 3D Tiles GD script implementation and your project file. So that's how the general build is structured. And how is that used? Well, very simply, it's just a whole panel where you have all of your options to add different assets, and then it adds certain nodes, which you can see over here. But really, there are like, I mean, we have more nodes. These are not all of them, but the ones that you have to care about are the Cesium globe, the tile set, and the overlay. So the globe is your reference point, basically. So it's like wherever you position the globe, your transform, that's where the center of the Earth will be, right? So that's really important if you're making like a game or an application where you care about persisting data between like cities and whatnot, then you should be aware of what your transform origin is. Then we have the terrain tile set, which just loads everything into the renderer. So you will find a lot of mesh instance 3Ds below here if you open that during your remote scene. I wouldn't recommend doing that. Then you have your raster overlay, which is essentially just texture data that will be applied on top of the models. And that will have a reference to your tile set. And we will see a demo of that in just a minute. Actually, just right here, I just read the note on the computer. Wow, I was smart to put that note in there. Cool. Okay, so I didn't trust the internet of the con. So I pre-recorded 2 videos that I would like to show you, but we will also do a live demo since it seems the internet is not that bad. Thank you, Microsoft. Yes. Yeah. Doing one thing right. Many things right. Please don't send any Microsoft people. Okay. Okay, so, geez, I feel like a high school teacher trying to play a video. Okay, cool. I think I just killed someone. No, something. There we go. Sorry, English is not my first language. So there we go. We spawn at a random position in the US. We're just moving upwards. We're just kind of taking a big look at the Earth. Just all of it is a giant 3D model. And so yeah, this is like 1-to-1 scale. We can zoom in, and here I had to memorize where Philadelphia was in the map. That was kind of most of the work. And there you can see like different LODs for the models spawning in. And then boom, there you go. You are now in Pennsylvania, and you have all of that model data, which is provided by Google. And yeah, all of those buildings actually do have collision, so you can properly interact with them. And they are raycastable. That took a while. And so yeah, that's one thing, and that's kind of like what we're sort of fronting with, the photorealistic tiles, because
You didn't go to Boston?
actually, so there's another, I mean, Boston, it's cool, but it didn't have the nice, like, show-off buildings. But there we go, we're in Boston right there. It's a different tile set. It's got OpenStreetMap buildings, and that's, if I'm not mistaken, that's the building that we're in right now. So, yeah. And yeah, you can like actually go straight in between buildings. So just to show that the collision calculation is all like very accurate and stuff. And so yeah, this is again another tile set, which would be the big map road with labels combined with OpenStreetMap's buildings. So that's the thing. It's not like you can just do one or the other. You can actually pick and choose which tile set, forget about OBS. You can actually pick and choose which tile sets you want and how to combine them, which I find to be really interesting because, I mean, if you wanted to, you could do like photorealistic tiles on Google Maps and then have OpenStreetMap's buildings, which would result in like some weird looking buildings. But I mean, that's something that you can do. And in the areas that Google Photorealistic Maps does not have buildings yet, you can load up OpenStreetMap's buildings and it will work just as well. There are higher definition tile sets. There's a pretty famous Denver tile set that's like really high def. And so yeah, you can import all of those in and they should just work fine. Now, if the demo gods will hear my pleas, I'm going to try and do a live demo. Emphasis on try. Let's see.
We're going to judge you very harshly.
Thank you. That gives me a lot of confidence. Okay, perfect. Here we are. So let me just move over that to the other monitor. And can you all see that? Well, okay, perfect. Okay, so this is essentially the same setup that we had. We had a Node 3D as the root of our project. We have the Cesium georeference, which just means the center of the Earth. And you might see for the geospatial nerds, we have ECF coordinates over there.
Is that the double precision build?
No, this is single precision build, but all of those values there are double precision. So you will get best of both worlds. Actually, I think all inspector fields in Godot are double precision by default. So yeah, you will get double precision. So that's why I had to separate them into like 3 different floats and not actually a vector 3, because vector 3s do compile down to be, compile down to a single precision. So yeah. So we have ECF coordinates for the GIS nerds. We have a scale factor, which will essentially shrink down the ellipsoid that you're in. And then we have latitude, longitude, and height, altitude, which is like a far more approachable kind of coordinate system than ECF. And yeah, so if we just press play on here, it should start loading. I did not really care about the lighting stuff all that much, but this should be the Vatican City. Yeah, there we go. And I loaded up, what?
Very topical.
And I loaded up just the Bing raster overlay, and yeah, there we go. We have all of the Vatican here, and it all comes streamlined pretty easily. And yeah, again, this is just like the default experience that that you should have, just like being able to create a scene and actually, you know, see everything render. I don't know what's going on with this one, but
It's the white smoke.
what? The white yeah.
It's in particle effects.
So is it doing a floating origin itself, kind of a thing? So it keeps the camera around 0?
Yeah, correct. So it keeps the camera at 0. Actually, you have the power to like control how that's handled. Over here, we have origin type on the inspector, so you can choose that to be a cartographic origin, which will do the floating origin, where your camera stays at the origin of the world at 0, 0 in engine coordinates, and then it will just translate all of the tiles one by one to your relative position. So that one is a little bit less performant than what would be true origin, because again, we have to translate each tile one by one, and that means translating nodes, right? So that comes at computational cost. You can also do true origin, but you will get shaky stuff when you get close to the surface. So that will not happen if you are in double precision builds. So that's why our suggestion is to do everything on a double precision build, but you know, you can just get the best of both worlds with cartographic origin. And so yeah, that's the geo-reference. For the tile set, we have some very basic properties. So we have maximum screen space error, maximum simultaneous tile loads, preload ancestors, blah, blah, blah. So all of this, what it basically means is how every tile will be spawned, at which rate tiles will be coming in, will be being fetched, and at what level of detail they will be. If you want my advice, just like keep this at 16. If you go 8 or lower, your computer is going to struggle, unless you have a very good computer. But yeah, I would recommend this. The default values are 16, so that's pretty neat. If you have a thread ripper, just go wild on the maximum simultaneous tile loads, and we can take care of that for you. And then otherwise, I would leave everything just as is. You can select to create physics meshes or not. We do our own custom physics, not system, but creation. But we will talk about that more in a little bit. And then you can select where you want to get your data from. So you can either get it from Cesium Ion, which is like the proprietary platform from Cesium that I was talking about, or you can get that from a URL. And this is basically so if you want to directly use the Google Maps API platform thing instead of Cesium Ion, you can definitely do that. But honestly, Cesium has like so many more capabilities and assets, and like it streamlines the whole process. But you can definitely do either one of the two. Also, if you're self-hosting something like a geo server, you can also get it from this URL. So that's pretty neat. And then we have our raster overlay, which just basically means what's going to render on top of the models as a texture. And so Cesium Ion has like these IDs for each asset that you want to build. So that's where I'm getting these numbers from. It's not just magic numbers, you know. Yeah, that's essentially the usage of the plugin. It comes with this like really nice Cesium Ion panel where you can be like upload your own data. You can check the status of your token, sign out. It's all saved in like your local cache, so you don't have to worry about accidentally publishing your credentials to GitHub. That's a pretty common problem. And then you can select from like the Ion assets. You can add a blank tile set, or add our dynamic camera, which contains that script that I mentioned we did for you. And this all works through like a authentication flow. Yeah, there we go. That went to the other screen, but essentially it just goes, hey, Cesium for Godot is requesting the following permissions, and then you just see it allow, and boom, successfully authorized. This is the most I've done on web development in 2025. Yeah, and yeah, there we go. We're authorized, and so yeah, that's essentially it. Okay, perfect. And so let's go back to. Oh, wait, did I? Why am I still on Godot? I am having. Yeah, there we go. Can you believe I'm a programmer? I can't. Okay, perfect. Performance. There's this like old adage in programming. I tried to track the source of it, but honestly I couldn't. That says you can't make a computer run faster, you can only make it do less. So again, I don't know who said that, but that's very, very true. And so, oh, 1 second, I lost my, there we go, okay. So Godot as an engine, just as pretty much any other general purpose tool out there, makes assumptions about how you're going to use it, right? And there's really nothing wrong with that if your goal is to be as helpful a tool as possible while still trying to remain a relatively blank canvas, right? So the Godot people don't really know what you're going to use Godot for, so they just like do a bunch of generalizations, and they're like, if that serves you well, that's great. If not, you kind of have to deal with it. So you can't make everybody happy, so you pick and choose your battles. We all do, right? So the first kind of like wall break that we hit regarding performance would be the node system. So in Godot, everything is a node, as I am well aware, you all know. So this is explicitly an inheritance-based model for behaviors. So of course, you can do some amount of composition if you do nested nodes, but this is different from other game engines because for things like collisions or physics, you really do need that extra node in there to be present on your scene 3. So also for any node to work, you must have an instance of that behavior in the scene hierarchy, and it obviously implies allocating infinite memory. But Godot already provides you with an arena allocator, so to avoid essentially calling malloc every new node instance. So that would be excessive, but there's still a couple of implications in terms of memory for nodes. So for each tile that we have in the world, and there are a lot of tiles, we need to generate 3 nodes, okay? So we need to generate, of course, the mesh instance, the collision, and then the collision shaped 3D. Which I am sure someone out there will be disagreeing with me about how this should be ordered, but that's how I ordered it. So it does not seem like a lot of overhead, but you know, nodes need to sync back to the main thread whenever they complete certain actions. So those great things that we all know and love and that we call signals, those have a performance overhead on the main thread. Those have to be called on the main thread to notify all other nodes that, hey, this particular signal that you were waiting for, boom, there you go. That's the result of that. So any mesh generation, for example, has to happen in the main thread. And thus this operation will not be able to be offloaded to the worker thread, which is where we handle all of the heavy tile fetching. So, yeah.
Why can't you generate meshes off the main thread?
You can generate the data for the meshes, like you can fetch all of the data for the meshes on the main thread. Like for example, if you get your vertex buffer, index buffer, and then all of your textures and everything, that can be calculated on a worker thread. But to actually add it to this scene and to actually have it like not rendered but ready to be there, like
It's
to
loaded onto the GPU effectively.
yeah, it's loaded on the GPU, but Godot constrains that function call to the main thread.
Gotcha.
Yeah.
So you're using a surface tool then? Is that what?
We're not using the surface tool because we found that to be a little bit less performant than what we eventually went with, which would be constructing an array mesh out of the raw components of the mesh,
Gotcha.
right? So yeah, we try to keep it as low level as possible so that there is the least amount of overhead as we can take from getting the GLTF to actually showing that to the screen. But the actual function to show it to the screen, it's bound to the main thread. So, you know, that's unfortunate. But yeah, the performance on the node system is really quite something. It's just the fact that we're instantiating a lot of stuff, and Godot wasn't prepared for that. So, yeah, it's not kind of a point against Godot or anything. So there is this one other node-based system that was kind of a pain to deal with, and that's the request system. So requests, sadly, are nodes as well. So every request, and those things that we do several per second because we cannot all have those cached. So every request being a node was really the most significant performance drawback that we found on this project. And you can have like nodes be, like request nodes be multi-threaded, but again, I mentioned how every node has to sync back to the main thread to be like, hey, I finished this work, right? So that little going back to the main thread and notifying all other nodes, that really takes up precious milliseconds. And so when you're doing thousands upon thousands of requests, that really, like, you can really take a hit from that. So the first time that we did that, like the first approach was, okay, I'll just have an object pool of nodes to avoid instantiating all those, and just like, I don't know, have 200 request nodes and then just use every request node every time that we can. That ended up not being really that great. So this is sort of the previous approach that we were taking, on which we have the render thread over here, we have our frame update, then we have signal synchronization. So it's a shame I changed the background last minute and now you can see like the arrows. But essentially, yeah, I know. Again, I said I'm not good at UI. So essentially you have two groups of worker threads, right? One to make your requests and one to actually generate your meshes from the results of those requests. So what you do is you go and make the request to the server, and those come back with some data, and then they go to the main thread and signal that synchronization, right? And then those call back to the request to the worker thread number 2, and then they actually start doing the mesh generation and transform calculations, which would be very heavy to do on the main thread. And then we make a bunch of deferred calls so that we can actually, you know, see what's going on in like the actual Godot representation. So these can happen on the same or different frames depending on when the request finished, and that's a really heavy workload. Any questions? Yeah.
Yeah, so you showed the nodes as HTTP Rust socking. Is this what it does now in the current plugin? Is this is in C++?
This is in C++, but this isn't what it does now. Was our previous approach with nodes. So just think of this one as like my whole pool of HTTP node requests. So yeah. So what do you do when the request system for Godot doesn't really like serve your purpose? Well, you go and build your own HTTP client, and that's what we ended up having to do. We have an underlying curl implementation of an HTTP client that can do multiple requests per frame. All of those in very nice organized threads, and so yeah, it uses like a pretty cool multi-threading model that I don't have the time to go into deeper now, but it's really interesting. And so yeah, this is a little bit of that implementation, but it's really straightforward. Any tutorial on how to build an HTTP client on curl will do. So now it looks like this, right? We still need the deferred calls, but these can be made in bulk to further reduce the amount of times we have to go back to the main thread. So essentially now we hit the render thread, we do the frame update, we do our requests on our first thread group, and then we no longer need to go back to the main thread to signal that we're done, because we're not nodes. Who knew that HTTP requests could be performant? I didn't. And then we do our callbacks to our second worker thread group, and that still takes care of mesh generation and transform calculations, and then we do our deferred calls, which, granted, still do touch the main thread, but now it's with less frequency than before. So since the amount of work can't be decreased because we can't just ignore requests that come through for tiles, we try to process everything in a way that's not too intrusive for the user. So if the adage was like, you can make a computer run faster, you can only make it do less. Now the adage should be something like, you can make a computer run faster, you can only make it do less, at least on the main thread, so the user won't notice. And that I'm taking credit for that one, if you all don't mind. And so yeah, that was our solution to the request system in Godot. Next up, there is just one slight performance hiccup that we found. Performance and actually gameplay hiccup, which are collision calculations. So great, now we can see the Earth, but we can go right through it. So that's not the ideal behavior that we wanted. As you can see, I'm like right through some mountains there. That's not what we want. How do we fix this? So Godot offers two types of collisions that can be generated given a mesh instance 3D node. We have convex collision, which uses a simple shape that aims to cover the volume of the underlying mesh. This is fast, but not so accurate. And it also, like Godot also offers tri-mesh collisions, which are granted more accurate, but again, those are a little bit slower. And I don't know if you can appreciate the difference there in the projector, but essentially here on the left, we have the convex collisions, which are approximations, and they are covering some space that shouldn't be covered by the collision. And then we have the tri-mesh collision, which just leaves everything exactly as the mesh is. So we know that there are other convex collision options that we can use, sort of like fast approximations to collisions, but they ended up overlapping too much anyways. So we went with the tri-mesh approach. Ask my QAs, they weren't happy when I was like, yeah, we can just get away with convex, right? Yeah, no, we can't. Okay, so how do we make collisions not take that much? Because, by the way, collisions can also only be generated on the main thread. So yeah, that's right. So yeah, we tried convex collisions for most of development, and the testers were not that happy about that. we have multiple cases of collider shapes overlapping a lot at street level where there's a lot of geometry close together. And sure, we don't go through objects anymore, but it also renders the usage of the plugin's very precise features unusable. So the only two problems with tri-mesh collisions is that collisions can only be created on the main thread, and that 3D tiles have a different winding order than Godot's imported models. So collisions are generated on the model's back faces. So essentially, you can go right through the earth, but you can't come back because the collision gets generated on the back faces. That's great. Okay. So the reason for that is that we're actually using a custom GLTF parser. We're not using Godot's parser because, again, performance. And we measured that. So yeah, that is tailored for, like, the GLTF parser that we use is tailored for 3D tiles. And so for the collision calculation, the first point, the last point, sorry, winding order. The winding order is basically the order in which vertices are picked from faces to form a, the winding order is the order in which vertices are picked to form faces on a particular mesh. So this determines which part of the model will be the front and which part will be the back. So here we have the common winding order, which is, how do you call this, clockwise? Yes, I think so. Yeah, and then you have counterclockwise, right? So Godot uses clockwise winding order for front faces of triangle primitive modes, and Cesium uses counterclockwise. So yeah, we had a little bit of a problem there, but since Godot has no built-in way to reverse the winding order of a mesh instance 3D, we can actually take advantage of this like weird little inconsistency between those two formats. And to create any collider, all we really need is to tell the physics engine what shape that collider is going to be, right? And in order to do that, what we can do is we can create our own custom collision shape with inverse winding order, so we can traverse the mesh in reverse, and then just reconstruct the collision. And that's what we ended up doing, and that's the entire implementation. It was very simple, but it took me like 3 hours to get right. And so yeah, notice there the reverse order of face point. And so yeah, at the end of it all, the concave shape will be passed to a rigid body 3D instance that we can create on another function when loading the tile. So at the end, it just looks like this, where you have, you just set the position, rotation of the instance, and then if that tile set has the create physics mesh option, you just, before you would just call deferred on the create tri-mesh collision, and that again would have blocked the main thread. But now you can just directly generate the tile collision with the inverse winding order. So that's pretty great. And now, if the internet gods will allow me, I'm going to show you some before and after stuff for these optimizations. Oh, sorry, I have Vimium. So there we go. That was before. And yeah, I don't think that would have been usable for pretty much anyone. At the end of the video, this is something that my boss sent me, so at the end of, at the middle of the video, he just opens up a chat with me. There you go, just ignore that chat. We're totally not gonna pay attention to that. But that just goes to show, and there's like even some tiles that we're not loading over here. So there are some tiles I just timed out entirely. And yeah, you can pretty much see this is not the ideal user experience. I don't know, this would make for a pretty fun like glitch game, but yeah, this was before collisions too, so. Yeah, that's pretty neat. Not embarrassing at all, by the way. And then we have a little after optimizations, which of course you already saw on the demo as well, but just for the sake of closure. There you go, that's after optimizations. And that just ruins so much smoother. And that's on the same machine too. So, and it's running on debug mode. This one is double precision. So there's just that caveat. But other than that, that's essentially it. So yay, optimizations. Who knew that we can make software be kind of nice? All right, so what's next? Of course, there are, this is a really basic implementation at the moment. There are still a lot of things that we could do to make this even better. So ideally, something that I would really personally like to do would be to ditch the node system altogether, or at least partially when we can, using the rendering server. Sadly, there's not a lot of documentation around the rendering server for 3D yet, so that's kind of left as an exercise to the developer, I believe. Then we have better tile interoperability. That just means more metadata, more API stuff that I can give you to access your data more easily. Optimized physics generation. The current approach is a bit naive, but I believe we can make that a lot better. And prettier sample projects, just like our own Atom engine right here. And so, yeah, that's really it. I don't know if anyone has any questions, comments, suggestions.
Clarifying one. So can you build the extension for double precision as well and still use it as an extension as double precision?
Yes, you can still, actually, we do have our GitHub.
'Cause that's even better, right? Like I'm happy to do a custom build for double precision for my stuff.
Yeah, no, but you can actually, so this is a repo. We actually just released like a week and a half ago, so woo! And this is, thank you. So this is the repo, and this is the README, and you can just as easily go in here and just add like, oh yeah, well, it doesn't say here, but you can just add precision equals double, and that's it. I think we have like a little part. There you go, double precision builds. So precision equals double, then you build Godot with double precision, and then you just modify the Godot 3D tiles.GDExtension to point to the appropriate DLL. And that's basically it. You just have to do that.
You tested on Windows?
Yes, so we've tested this on Windows. So far, this is only available on Windows as a development platform. We do have plans to release it to Linux and macOS. Actually, this morning, I woke up to someone on the Cesium forums sending me a direct message about opening a PR for a macOS build. It seems they already have it pretty much working, so that might come earlier than expected. Yeah, so that's it. Yeah, the beauty of open source, right? So, and also, if you're totally welcome to just come in here and open a PR. Yes?
There was, earlier in the slides, there was a thing that mentioned that it was performing well in debug mode. Do you see a significant boost in performance once you're in release? Or?
Absolutely, yes. There is a very significant boost in performance on release mode. That debug mode was running on a double precision build, so that takes away some of the stuff that we need to do floating origin. So that's why it performed comparably to release mode. But yeah, release mode flies sometimes, so yeah. It obviously depends on the tile set that you're working on. You're not going to load all of the buildings in Tokyo in like 1 second. That's ambitious.
Hey, I have another question. Basically,
Yep.
So there are certain projects that I've seen that like have used the rendering server to great effect, and I think like it's really great. Do you think that there are going to be any use cases where you're really actually getting a benefit out of using like individual nodes? Like maybe like, oh, I want to save this mesh for whatever reason.
Yeah, I can see that being.
All of that is solvable in rendering server, and basically like everything should ultimately go that way.
I can see that being the case, especially for things like if you want to save a particular scene with like some geospatial data, and you don't need it to be that dynamic, you can just save the meshes as they are, and you get rid of all of the performance fallbacks with that. So that's definitely something that you could do. But yeah, we aim to do rendering server almost 100% of the time. Yes, back there.
How does that look on mobile?
how does that look on mobile? That is a great question, and I actually have an issue here open for it. Yeah, on which you will see that I basically answer. So yeah, I haven't tested this on mobile yet, but I'll be sure to update this issue once we do actually test on mobile, because there seems to be a lot of interest, especially in the virtual reality kind of space, to get this on. So yeah.
It's not a question, more a suggestion. So you said at the last slide that you want to use the rendering server directly, which is a good idea, but you can also use the physics server directly, so you don't actually have to use the collision mode. You can just add the collision shapes directly to the physics server, which is multi-threaded as well. So you could get away with just single node for each tile, and then you can add both the rendering data
And the collision data all crammed into the server's APIs instead of the nodes. Is that okay? Yeah, absolutely. We can take advantage of that, and that is why, in the end, there we have a little space for optimizing the collision generation. We're aware that there's a lot of work that could be done, especially using Godot's lower level APIs, and we hope to utilize that to great effect in the near future. So yeah.
Are there any examples for hosting your own 3D tile data anywhere?
I think you're most likely going to find that on Cesium's platform and on their forums and something like that. Not exactly on the extension itself, but anything that could work with Cesium does work with the plugin. So
Okay.
yeah. Any more questions, comments? Alrighty, perfect. I went over by 1 minute. Sorry about that. But yeah, that's it. Thank you.